Perfect. So let's get started. Hello, my name is Andrew. I'm the product manager at Airbnb for machine learning infrastructure, as well as a fairly new team called Applied ML. And today I'll talk a little bit about Bighead, which is Airbnb's end-to-end machine learning infrastructure. Out of curiosity, how many people know about Bighead or have heard about it? Nice. Yeah. Nice, actually, creator of Airflow. I'll talk a little bit about Airflow, so maybe that'll go through. So I'll cover a little bit about Bighead, and hopefully I can kind of share how Airbnb thought about machine learning infrastructure and how we build a solution for it. And I'll talk about how we plan on open sourcing it and give a little bit of description there. So the general agenda is background information to start off with, design goals, what were the design goals put in for our infrastructure, architecture deep dive, and then talk a little bit about our open source plans, and then I'll open up for Q&A. Background. So how many people have stayed at Airbnb? That's awesome. I would have been heartbroken if there was only a couple of hands. So you guys are probably pretty familiar with Airbnb and the product. It basically is a global travel community that offers magical end-to-end trips, including where you stay and what you do and the people you meet. Airbnb is already driven by machine learning. So these are three use cases that have historically existed at Airbnb for quite some time. The first one is obviously search ranking. How do we make sure that users get personalized search results? And this has existed for quite some time at Airbnb, as you can imagine. Smart pricing. How do we make sure that hosts have intelligent pricing choices for when they list their homes on the platform? And then fraud detection. It's a constant battle, I think, for most companies and the companies that you work at to fight fraud. And so we've imbued it with machine learning to make sure that we have models that can help us detect when a user is putting up a fake listing or whether they're trying to hack into another account. And so historically, these three teams have built their own machine learning infrastructure. But we found that there are many more opportunities for ML at Airbnb. There were opportunities within paid growth. How do we use a model to better identify where we put our money and how we can grow the community? How do we identify different room type categorizations? And so you can imagine, because Airbnb has such a vast number of images of homes, things like detecting whether something is a bathroom or a living room actually can play out pretty large roles within the company. And so one example is if I'm doing automated ads, I really don't want to show 5 pictures of a bathroom. That will really lower the click-through rate. And so overall, these models that do kind of these interesting things have large value and business impact for the company. And it continues on to listing photo quality, object detection for amenities, even our kind of business unit of Airbnb Plus. And so when we're thinking about the machine learning infrastructure, we broke it down into 2 complexities. The first one is the intrinsic complexities. These are the complexities that are fundamental to machine learning, such as understanding the business domain, selecting the appropriate model, selecting the appropriate features, and fine-tuning the model. However, we did find that there was quite a lot of incidental complexities with machine learning. This is integrating with Airbnb's data warehouse, scaling model training, scaling the model training as well as serving, keeping consistency between your prototyping versus production, your training versus inference, keeping track of multiple models, different versions of the models, different experiments you run with the models, as well as supporting the iteration of ML models. I'm sure all the ML enthusiasts here have built and iterated upon many models, and so that's a fair point, that you spend quite a lot of time iterating on it. And so on average, we found that it takes about 8 to 12 weeks to build a model. And these ML workflows tended to be slow, fragmented, and really, really brittle. And so the ML infrastructure team was born to address these challenges. First, with its vision, we wanted to see Airbnb routinely ship ML-powered features throughout the product. And our mission was to equip Airbnb with shared technology to build production-ready ML applications with no incidental complexities. This is a little bit of the pinwheel effect for models. I hope everyone can see that. But essentially, it goes into, you start with your prototyping within Redspot, and you first start with data management, you go into your prototyping, and then you go into model lifecycle management, and then productionization, and you kind of iterate through. Our goal was to provide infrastructure to make this pinwheel effect a lot faster, so that we can basically speed this iteration cycle for all our ML users of the company. Okay, Bighead design goals. So 4 design goals we focused on: seamless, keeping things seamless, versatile, consistent, and scalable. Seamless, is it easy to prototype? Is it easy to productionize? Same workflow across different frameworks. Second, versatile. Do you support all major ML frameworks? I'm sure everyone here knows probably 3 or 4 different ML frameworks that are all very, very popular. And so how do we make sure that the Airbnb community can leverage what they want to use rather than forcing them to a single framework? Does it meet the various requirements? Is it online or offline use case? What's the data size? SLA, service level agreements. Does it require GPU training? Is it scheduled or is it ad hoc? And then consistency. Consistent environment across the stack, as well as consistent data transformation, prototyping and production, as well as online versus offline. Okay, scalability. Is it horizontally scalable? Is it elastic so that it can grow with different scaling challenges? As you can imagine, Airbnb is a very seasonal business, and so we do find that at different time points there are spikes in traffic, and so we do want to make sure that we build something scalable if it influences the Airbnb platform. So we'll dive into the architecture deep dive. So this is essentially Bighead in its essence. Oh, over there. You can see that it's made up of about 7 components. I'll talk about each component, and I'll talk a little bit about why 3 of the components are kind of spread across the architecture. So we'll start off with Redspot. So Redspot is basically prototyping with Jupyter notebooks. So Jupyter notebooks, what are those? Why are they so important? It really lets you interactively run Python code. It lets you kind of build what we like to call research reports. And we do find that a lot of ML engineers, as well as data scientists, like to keep track of what they've tried. Because as important as the end model is, it's also important to keep track of what you've tried and making sure that you're developing and iterating on it so that you can show your work to others. But just Jupyter Notebooks, is that enough to actually make it a good ML prototyping environment? So it has the interactivity and feedback, but it also needs access to very, very powerful hardware, as well as access to data and the data warehouse. And so what is Redspot? Redspot is a supercharged Jupyter Notebook service, a fork of Jupyter Hub project. It's integrated with our data warehouse. It has access to specialized hardware, such as GPUs. It does file sharing between users via AWS EFS, Elastic File Share system. And we like to promote all of this kind of shareability within the platform because we want to make sure that the Airbnb ML practitioners, which is not too large of a community, at least have the ability to share their work across. And it allows them to actually share their work across a broader audience as well. And it's packaged in that familiar Jupyter Hub UI. And so this is a look about the UI we have. You get to choose your Jupyter environment. You get to also choose your Docker image so that you can actually customize your Docker image. And I'll talk about the Docker image service and how we maintain consistency throughout our entire infrastructure through it. And then on the second panel, you can see that you get to choose your instance type. So how does it actually promote the kind of qualities that I mentioned before? It's consistent because it promotes prototyping in the exact environment that your model will be in through the use of Docker images. It's versatile because it has customized hardware where you can choose different type of AWS instances, EC2 instances. And then it's seamless because it's integrated with Bighead service and the Docker image service, we'll talk about a little later. And it leverages the Bighead APIs as well as the different UI widgets that are built within Bighead. Cool. Next, I'll talk about the Docker image service. So the Docker image service is the environment customization. So why did we actually build it? ML users have a diverse, heterogeneous set of dependencies, as you guys are pretty familiar. They need an easy way to bootstrap their own runtime environments and need to be consistent with the rest of Airbnb's infrastructure. So why is that so important? If you build your model in a certain environment and it turns out you're productionizing it on something else, let's say different dependencies, or even the versions mismatch, it can cause very, very strange behaviors. And so we wanted to make sure that we kept this consistency, and this kind of led to the beginning of the Docker image service. So Docker image service is the dependency customization, our configuration management solution. It's a composition layer on top of Docker to make it easier to build your Docker images. It includes a customization service that faces our users, and it kind of promotes that consistency and versatility. Next, sorry if I'm rushing through, I'm just trying to fit it in just because I accidentally put in 60 slides. So Bighead service. What is Bighead service? It's the model lifecycle management service. So why is model lifecycle management so important? Tracking ML model changes is just as important as tracking code changes. ML models is no longer just code, it's also the data you put into it, as well as how you've trained it, the dependencies. And so tracking all of this is very, very important for ML models, and it reduces any type of incidents or accidents that could happen when you're deploying something to production. An ML model needs to be reproducible and sustainable. We found that it's pretty key to make sure that ML practitioners throughout the company had an easy way for them to actually keep track of what they've done, and we are able to basically take all the dependencies, all the different metadata regards into the model, such as the model performance, as well as the code, and just kind of version it for the users. As well as you can compare experiments before you launch it into production, which is crucial and critical. So this is actually, we just recently updated our UI, and I didn't get to put another Git or GIF. I don't know which one you guys choose, but essentially the flow is still very similar. Essentially, this is the UI where you get to choose your model, you get to choose the different versions of the model in terms of when it was trained, whether it was ad hoc or scheduled, and then you get to deploy it. It has links to the version Git shell, so you can look at the code that it was used to create the model. And this is all a service that we build for model management. So what happens if it goes wrong in production? We know that it's never perfect, and so in the end, we still have links into the Kubernetes dashboard, so you can debug. We also have different metrics that are emitted to make sure that if you do have a model in production, you can still track whether the model is still serving traffic. And then further on, we want to explore if we can do score drift, just to make sure that if there is a tremendous drift in terms of the scores that are being returned, we can alert users as well. I'm going to skip the video for now. Okay, Bighead service, how does it promote the themes that I mentioned before? It's consistent, it's a central model management service, and it's a single source of truth about the state of a model, its dependencies, and what's deployed. It's also seamless. It's context aware of visualizations that carry over the prototyping experience, and so you can actually use the visualizations in your red spot instance, as well as port it over into Bighead service so that you have the same type of visualizations and you can use it across the board. Okay, Bighead library. So ML models are highly heterogeneous. We found that pretty much we've seen usage of every ML framework at Airbnb. And there are many frameworks out there, and so we find people using TensorFlow, PyTorch, Keras, XGBoost, Spark, everything. And so frameworks are very heterogeneous, as well as it's heterogeneous in the training data. The data is very different depending on what kind of model you have. If you're building an NLP model, or if you're building just a simple logistic regression, or if you're going with computer vision, the data that you're using to train on and you're scoring on is going to be very different across the board. And then the environment is also very different. Depending on how heavy the model is, it might require GPUs, or you might be able to parallelize it on CPUs. And the dependencies are very different across the board as well. So ML models are really hard to keep consistent. Data in production is different from data in training. Offline pipeline is different from your online pipeline, and everyone does everything in a very different way. So what is the Bighead library? It's essentially, we built a pipeline on steroids. It's a compute graph for pre-processing, inference, training, evaluation, and visualization. It's composable, it's reusable, it's shareable. It has wrappers across the popular ML frameworks such as TensorFlow, Keras, PyTorch, MXNet, scikit-learn, XGBoost. It has fast primitives for pre-processing. We've built some rebuilt some that were in Python and C++ to make sure that we had a lot of gains in performance, as well as it has the metadata for the trained models, and we can actually save that metadata and bring it back into Bighead service to track different statistics of your model as well. Consistency, it has a uniform API, it's serializable, and it's the same pipeline used in training, which is used for offline inference and online inference. And so this is really key, that the code that you write for your training is going to be identical to the one that you're using in offline inference and online inference. And we can maintain that consistency through Bighead and the Bighead library. Cool. So this is just a simple pipeline. Up top, you can see that we specify the categorical features and then the numeric features, and then you initialize your pipeline, and then use, for the numeric features, we actually do a nan to mean, and then for categorical features, we do a hot label encoder. And then you actually chain on your XGBoost classifier, so you set different hyperparameters, and then you have your ML model, and you can kind of run that in training, as well as you can run it in production, and you're guaranteed to have it consistent. And so this is just a visualization of that pipeline. We actually, so this is a little bit outdated, but at the end, we usually have the XGBoost classifier at the end, showing that as well. And it's easy to serialize and deserialize your model. So you can actually serialize and deserialize your pipeline. And this is a visualization of the training data. Okay. And the transformer. Cool. So deep thought, online inference. Okay. So it's hard to make online model serving. Why is it so hard? It's hard to keep consistency with your training data. Usually it's different data that's going online and online and training. It's usually a different pipeline as well, what you're delivering in the production and what you've built in training. It also might have different dependencies if you don't keep track of it clearly. It's very difficult to do, and so data scientists can't launch models without an engineering team backing them. Engineers often have to rebuild the models. I've seen many times when a data scientist will have the model ready, however, it's not production ready. It can't deliver inference in sub 30 milliseconds. That might affect production time, so a lot of engineers might have to rebuild the model and try to keep it consistent. And these are problems that we have seen before. It's also hard to keep it scalable. It's easy when you're running a model locally and you run a couple requests to make sure that it's going properly. It's hard to see what happens when you put in production traffic. As traffic scales into the thousands, hundreds of thousands, millions per second, you need something that's scalable and dynamically scalable, because models all don't receive the same traffic, and so you need some kind of infrastructure that's highly scalable for different types of throughput. And throughput fluctuates across time. So how does deep thought really showcase the three characteristics? It's consistent. Through Docker and the Bighead library, it's the same data source, pipeline, environment from training, so you can make sure that we have that consistency for how you train to what's actually being scored in production. It's seamless. It integrates with event logging and the dashboard. It also integrates with Zipline, which I'll talk a little bit about later. And it's highly scalable. It's built on Kubernetes. The model pods can easily scale up, so we can actually scale up for dynamic traffic and scale back down if there's not a lot of use. And there's also resource segregation across the models, and so you have no noisy neighbor problem where one model can actually influence the behavior of another one. This is an architecture diagram of how deep thought was built. It goes to the REST API. We have a model manager to make sure what actual models are registered within the Bighead service. And then we actually route the models and the model traffic to the correct Kubernetes pods that host those models. And we do load balancing to make sure that we don't have any type of hot pod that's getting all of the traffic. ML Automator. So ML Automator is for offline training and batch inference. ML Automator, why do we need it? Automated training, inference, and evaluation are necessary. It has scheduling, resource allocation, saving the results. You can set it up with dashboards and alerts, and you can orchestrate these type of events. So ML Automator, how does it showcase a lot of the kind of qualities I mentioned before once again? It's consistent. Like Deep Thought, it uses the same Docker image as well as the Bighead library to make sure you have that consistency. It's seamless. You can automate tasks via Airflow. Airflow creator, Max here. Yes. You can actually automate tasks via Airflow. You can generate DAGs for training, inference, etc. with the appropriate resources. And it also integrates with Zipline. And I'll talk a little bit about Zipline in a few minutes. And it's highly scalable. And so after Airflow orchestrates, you can actually run it on Spark for distributed computing across large data sets. And this is just a look at the DAG, where ML Automator has kind of scheduled the job. Okay, Zipline. So Zipline is the ML data management framework. Feature management is incredibly tough. This is probably one of the toughest components we have to build. I'm sure a lot of people who are in ML today know that feature engineering is probably the hardest part about ML. At least the most amount of time is spent there, and we found the same thing. And so we found that it's incredibly difficult with keeping consistency between your offline and online data sets. It's tricky in generating your training sets that depend on time correctly, especially when you're running ETL jobs that do daily aggregates. You need that intraday timestamps. It's slow in training as well. Slow training gets sets in backfill. So basically, backfilling all the data takes quite a lot of time. It has inadequate data quality checks or monitoring. So what happens if your features start to drift, especially for an ML model? Do you need to retrain it? And it's also very unclear in terms of feature ownership and who owns it, as well as how you share features across the company. So we've embarked and built Zipline. Zipline is consistent data across training and scoring. It's consistent data across development and production. It has point-in-time correctness across features to prevent label leakage. It's seamless and integrates with Deep Thought and ML Automator, and it's scalable. It leverages Spark for batch and Flink for streaming workloads. And so this is just a very simplified view of how kind of we've thought about the problem and to communicate the problem, especially between your training and online scoring. So online scoring, you have data in your production data stores, and it's going to be used as the features for when you're doing real-time inference. However, a lot of the data you use to train is things that have gone to the data warehouse, gone through multiple ETL jobs. And so you find that there's a pretty big inconsistency between the data you see in production as well as the data you're using to actually train your models, because the data you're using to train your models is so multiple magnitudes different from what you're seeing in production. And you also lose that point-in-time correctness because most data warehousing schemes do our daily aggregates where they actually just drop a lot of the intraday timestamps. And so if you're building a search personalization model where you want to see where people are clicking and their movements to give them a better personalization of what homes they might be interested in, that intraday event could be lost. And so we've kind of solved it with Zipline, which looks to get a lot of the data as upstream as possible from mutations and events. And it'll actually create a standard set of data, feature data, that can be used either for your online scoring as well as training, so that we can keep that consistency across the board. So this is the big summary. Bighead is the end-to-end platform to build and deploy ML models to production. That's seamless, versatile, consistent, and scalable. It features model lifecycle management, feature generation and management, online, offline inference, pipeline library supporting major frameworks, Docker image customization, multi-tenant training environment, and it's built on a lot of open source technology: TensorFlow, PyTorch, Keras, MXNet, scikit-learn, XGBoost, Spark, Jupyter, Kubernetes, Docker, and Airflow. And it's fairly complex. And so, for last minute, we are planning on open sourcing it. We're moving towards actually partnering with our first couple private collaborators. And so if you are interested, please email me or message me on LinkedIn or reach out to me, because we're looking for the first couple kind of private collaborators to go and kind of make sure that this is useful to the public as well, and kind of go through the steps of making sure that we're ready also to open source. For the first open source project, we're actually going to open source what I mentioned: Deep Thought, ML Automator, Bighead service as a core workflow, and then we'll expand it to the other services that I mentioned, which is Zipline, Docker image service, RedSpot, and so on. Cool. We'll open it to questions.
This is a fantastic talk. Any questions?
Oh, there's a question back there.
Sorry. Short arms. Any idea on the timeline for when you'll be open sourcing?
Great question. So we did say that we were going to open source earlier this year, but we had to push it back because of, as Airbnb is getting ready to IPO, we've had a lot of work come our way, yeah, as you can imagine. But we're looking for private collaboration in this quarter, so Q2 2019, and then Q3, Q4 is when we're going to kind of make the steps into opening up more broadly.
And so what would you be looking for in a private collaborator?
Yeah, so private collaborator.
Besides me, specifically.
So we're scoping private collaborators just to kind of one or two companies, and we're really looking for a close-knit partnership where we can kind of meet and basically flush out a lot of the details, just because it's a massive amount of code, and we imagine it's not easy to onboard onto it. And so we also are looking for similarities in tech stack. And so we are built on AWS. We use a lot of these technologies such as Docker, Kubernetes, we use Spark, Airflow, and so similarities in tech stack is also something we're looking at. And even just proximity to us in our headquarters, just because we imagine we'll meet very frequently, that's also playing in. And so there's a lot of things, but if you're interested, please reach out. Yeah, happy to talk more.
Andrew, actually, I got a question. On your Ziplines, the feature engineering repository,
Yep.
what tech stack is that? Is the data stored on Hive or is no?
Airstream, but it's mostly through Hive. And so you can actually access it through Hive. You can also access it through Spark. So it's just kind of underneath the hood. It's just XGBoost.
But if you're using Hive, you cannot, supposedly adding new features, you had to go backfill all the data.
So for the new features, we actually go more upstream, and rather than going through Hive, we look to get the mutations from basically all the production data stores. And so the MySQL production data stores, we actually extract the bin log and the mutations, and we get a stream of mutations so that essentially we can replay the mutations to get any point in time. And so we use mutations as well as we use what we have, which is kind of just Kafka events. We also store those as well. And so essentially, in order to have point-in-time correctness features, we need the raw mutations, and that's what we're kind of doing. Yeah.
Any other questions? Any questions? Oh, this is a surprise.
Thank you so much.
Thank you, Andrew.